Aina, the exam is getting closer and I'm feeling nervous.
I'm nervous too. I've been studying, but I really don't understand chapter 3.
Oh, you don't worry because I actually understand chapter 3 quite well, but honestly, I'm struggling with chapter 5. Can you teach me?
I understand chapter 5. Later, I will teach you.
Deal. I teach you chapter 3, you teach me chapter 5.
Okay.
Okay. Let's move to the chapter 3 first, memory hierarchy and cache design. We'll look at how computers manage data to ensure processor is not left waiting. Modern computer architecture is a balancing act. We need speed, but we also need high capacity and low cost. To achieve this, we use hierarchical structure. The core principle is simple. The fastest, most expensive memory stays closest to the CPU, while larger, slower components sit further away. This hierarchy is broken into 4 main levels. First, register is the smallest and faster units located inside the CPU for immediate data access. Second, cache memory, a high-speed buffer between the CPU and RAM that store frequently used data. Third, main memory is a primary storage for active program. It is larger but slower and volatile. Last, secondary storage. Largest capacity for long-term retention, for example like SSD and HDD, but has the slowest access time. So, how does the system decide what to put in the fast cache? It uses the principle of locality. First, temporal locality suggests that if you used a piece of data recently, you will likely need it again soon, like a variable in a loop. Second, spatial locality suggests that if you use access one address, you will likely need the address near it shortly, like reading through an array. One common way to organize this is direct mapped cache. Here, every block of main memory has exactly one specific home in the cache. To find that home, we use a placement formula. The memory address itself is partitioned into 10 bits, a line number, and a byte offset to help the hardware quickly locate the data. Finally, let's look at how this performs. When the CPU asks for data and finds it in the cache, it is a cache hit in immediate access. If it is not there, it is a cache miss and we must fetch it from the slower main memory. As you see in our example, the first time we request block 5, it is missed and gets loaded into line 1. But the second time we ask for it, it is a hit. This simple mechanism is what allows modern computers to feel snappy and responsive despite the massive amount of data they process.
Chapter 5, Machine Level Representation of Data. Computers use the binary system 0 and 1 to represent data, unlike humans who use the decimal system 0 to 9. Computers also use the octal, base 8, and hexadecimal, base 16, to make data easier to read and work with. The way to convert binary to decimal is we multiply each digit by powers of 2 starting from the right. To convert decimal to binary, we divide the number by 2 repeatedly and write down the remainders. Then we read the remainders from bottom to top. To convert decimal 202 to hexadecimal, we divide by 16 repeatedly and write the remainders. In hexadecimal, 10 to 15 are A to F. Reading the remainders from bottom to top, 202 in decimal becomes CA in hexadecimal. To convert hexadecimal 3A to decimal, we multiply each digit by powers of 16. A equals 10, so 3 multiply 16 plus 10 multiply 1 equals 58. Therefore, 3A in hexadecimal equals 58 in decimal. Okay, now, to complement representation with an overflow example. To complement is how computers show positive and negative numbers in binary. To get a negative number, write the positive number in binary, invert the bits, and add 1. A 32-bit floating point number has 3 parts: sign, 1 bit for positive or negative, exponent, 8 bits, which shows the power of 2 with bias 127, and fraction or mantissa, 23 bits, which stores the decimal part of the number. And you can watch the example I display on the screen. We move on to the next. How data is represented affect performance and memory. Different types use different number of bits. Integers are faster because CPU handle them easily, while floating point numbers are slower due to extra steps like normalization and rounding. That's all from me. I hope you understand.